of Rochester, Jim Boyd, who will introduce tonight's speaker. So take it away, Jim.
All right. Yeah, hi everybody. I'm Jim Boyd, president of the MIT Alumni Club of Rochester, New York. I first learned of Dr. de Wit from a newspaper quote that he gave just after the first images from the Webb telescope were broadcast. And his quote was about, the importance of this telescope in really enabling kind of the next step in interplanetary research and exoplanet research. And, I thought, wow, that sounds so cool, right? I'm a child of the 60s and 70s, and I grew up with Star Trek and Lost in Space. And it's like, wow, I got to meet this guy and convince him to talk to us. And so, so here we are. So, Dr. Julien de Wit is an assistant professor in the Earth and Planetary Sciences department at MIT, where he leads the Disruptive Planets Group. This group's mission is to discover and study new worlds to consolidate our understanding of planets and habitats. Julien received his Master of Research in Astrophysics and Master of Science in Aeronautics from ISAE, France in 2010. His Master of Science in Aerospace from University of Liege, Belgium in 2011, and a Ph.D. in Planetary Sciences from MIT in 2014. Additionally, he received the Pioneer of the Year 2017 and Innovator of the Year 2017 of MIT Review's Innovators Under 35. So with that, I take it away, Julien.
Hey, thank you. So I see that we have a nice small group. So what we can do today is I'm going to go through my talk. I'm going to skip some details so we can really keep that a conversation. So if you have a question at any time, please unmute and we can really have that conversation. So let me start sharing my screen if it is okay with you. And today's talk is going to be entitled Entering a New Era of Space Exploration with the James Webb Space Telescope. I'm not going to talk a lot about what we're doing in the group because that would be a talk in itself. I'm rather going to be bringing you through the why, how, what, buts of the new era of space exploration with James Webb. We're going to start with the why. Why is it totally okay and justified to be excited based on where we're at? Why is it that this new era of astronomy matters so much? Then we're going to go to the how. How did we get here? We're going to do a bit of history, talk about some technical development, and then talk about how James Webb and exoplanetary science truly are game changers. We talk about what lies ahead of us, and specifically what we would be able to say about the climate of other world, exoworld, world beyond the edge of the solar system. And before wrapping up, I'll talk about the but we still have quite a bit of homework. There's still a lot of work to be done in order to really make the best of these multi-billion-dollar facilities, the James Webb Space Telescope, but also the extremely large telescopes. All right, let's get going. So why being excited and why does it matter? Well, why does it matter? Since, for a long, long time, humans have had a very special relationship with space, the universe, space exploration. And as we are getting more crisp perspective on the universe through technological development, we have the opportunity to bring back on the table topics that are really close to us. For example, 10, 20 years ago, it was very unlikely that you would find papers that you would credit to be of some form of authority discussing life in scientific journals. It is not the case anymore, owing to technological development. Now that we find planets that may be habitable, that we find planets for which we have the technology to study the atmosphere in great depths, we can bring back or gain new perspective on the concept of habitats, life inhabitability, as well as climates, and potentially refine our own climate model, the one that we apply here on Earth. So the crisper the perspective we get of worlds beyond the edge of the solar system, the more we can relate a broader part of the population to the research that we do and the finding that we get to. And in that context, I'm going to highlight a class that I revamped together with Rick Binzel a few years ago. That was 12,400-hour solar system, and now it turned into 12,400-hour space odyssey, that really provide that space to the student, the space where we can reflect on the humanity's development through space exploration and reflect on what it would mean for us as a species to find life elsewhere, to become a multiplanetary species, because this is really what we're looking at in the next decades or the next century. And why am I finally able to do that? Well, because back in 2017, thanks to a consortium with the University of Liege, we found the very first, and still today, the only planetary system that hosts temperate terrestrial planets that can be studied in great depths, so around which we can search for signs of atmosphere, signs of habitability, and maybe even potentially inhabitability. And this is the TRAPPIST-1 system that I'm showing here. That is, can you see my my mouse on the star? Just in one hand nodding. Anyone?
I do not, no.
Do not. That's not going to be great if you cannot see that. Let me see if I can do. Ah, all right. Then I'm going to have to annotate from time to time and then clear my annotation. Oh, okay.
Now I can see the mouse, yeah.
Now you can see the mouse.
It's very small, yeah.
And now it's moving all over the place. See, that's the one thing that we didn't test before. If I do annotate, then you'll be able to see it. Good. I'm just going to clear my annotation along the way. And it's okay. It's live. All right. So this is a star. And the star is of particular interest because it's about 10 times smaller than the sun, allowing for a whole suite of planets, 7 of them, to be compacted next to it while still being potentially habitable, but at least temperate. As you can see, the green zone is what we'll call the habitable zone, which is shown here around the sun. And you can see that you have a whole suite of 7 planets, terrestrial, compacted in this tiny area, which is substantially smaller than even the orbit of Mercury. All right. So the beauty through this discovery is that we can, of course, have an opportunity to search for life around other stars than our sun, but also revisit our understanding of planetary system. Because so far we've studied a few planetary or terrestrial planets, Venus, the Earth, Mars, and Mercury, and now we have 7 of them in completely different configuration. Just to give you an idea, planet B turned around its star in about 1.5 days. Planet H is in about 20 days. So very, very different configurations. So this is what we can gain when we start looking elsewhere, but also when we make this discovery, we have the opportunity to have a foundation upon which discussing actually looking for signs of life in the next decade. And you'll see how James Webb plays a role in that context. Oh, it's going to be fun, playing between annotation and moving slides. Okay. All right, so naturally this discovery made the news, and through making the news, it became completely fine. It was fine before, but now, you know, it was all over the news talking about life elsewhere. So this is a platform that these scientific discovery provide us with, hence can also allow us to start the classes that I was discussing before. But the beauty of space exploration here at the beginning of the 21st century is that searching for life is also happening much closer to us. On Mars, on Enceladus, possibly Europa, and even, I'm sure you heard, in the clouds of Venus. So there really is a good reason to be excited. And this really matters. It helps us understand what are the key concepts that support the societies that we build, habitats, life, potentially even intelligence. And another reason to be excited, if we zoom and we even move beyond planetary science, we can highlight that on the year we found the TRAPPIST-1 system, 2017, on that same year, the community made the first discovery of an interstellar object, an object coming from the outside of the solar system, coming through, and first discovery of the gravitational waves, which were predicted close to 100 years ago. So that gives you an idea, or it highlights the fact that we are awakening at a faster and faster pace to the universe, thanks to our technological development. So there's a lot to be excited about, not just in planetary science, in the field of astronomy, and obviously in other fields as well. Okay, now, how did we get here? A bit of history, and how are exoplanetary science and James Webb's game changers? If you have questions, don't hesitate to interrupt and ask them, of course. All right, so I don't want to say that everything started in 1995, which is the year where the first planet around the main sequence star that isn't the sun was discovered. It started decades before that, and a lot of technological development went into supporting this discovery. But this discovery enabled the first and only so far Nobel Prize for a field for the discovery of that planet to the Swiss Michel Mayor and Didier Queloz. And I'm going to talk to you about discoveries since that point, or around that point, late 1980s, early 90s, through today. So what you see here are planets that are plotted. So you have mass, orbital period. In red, just for reference, you have the planet in the solar system. And then for the other plots, hopefully you see my mouse, you have planetary radius versus orbital period. I'm going to move forward in time just to give you a sense of what we found. So progressively, just a handful of them. For them, we mostly had their mass. In 1999, we had the size of one of them. And you see that the information we get relate to the technique we use to detect them. And I'll get to that on the next slide. Moving forward, 2005, 2010, today. So what you can see is that, first of all, there really aren't that many planets that look like, or that are in orbital configuration similar to what we have in the solar system, right? Finding these planets that are far away from their star is a challenge. That's step one. Step two, you can see that there's a bunch of them, about 5,000 planets found in about 4 other planetary systems that are our own. So the sample of planets that we have has increased, and you'll see that it will have consequences on the perspective that we gain on this planetary system. That's a disruptive potential of exoplanetary science there. Let's skip that. And you can see that we found new planet types. For example, this ensemble of planets in the red rectangle are called hot Jupiters. They are planets that have the same size as Jupiter and Saturn, but instead of turning around their star in 11 plus years, they turn around their star in only a few days. Very different configuration. As well as super Earth, which are actually 2 sets of planets in this blob. They are super Earth as well as mini Neptune. There's a valley. And if you want, I'm happy to talk more about that towards the end of the talk. So exoplanetary science is a game changer for planetary science and potentially astrobiology, because it provides us with an ensemble of systems through which we can move past this unique and century-long perspective that we've gained through the planetary system that is ours, the solar system. So we find planets that are unexpected, like gas giants that are really close to their star, even though it's really difficult to form them there, because as soon as the star kicks in, turns on, it starts clearing the gas in the disks. So most likely they have to form far away and then somehow migrate really close to their star in some processes that have not occurred in the solar system. We find planets without star, free floating to the galaxy. We find planets with multiple stars, like Kepler-16b, that has 2 suns and offer iconic sunset like Tatooine in Star Wars. In fact, there are even, I think, a few with 3 stars and one with 4. So that's the type of system architecture that we find completely different to what we used to. We find planets like J1407b that has 37 rings, about 200 times the extent of Saturn's ring. So big that if Saturn had such a ring system, it will be bigger and brighter than the moon in the sky. And we find planets...
I want to point out that that was a product of the University of Rochester there. The image there. For the locals.
And we have found planets literally dying around their star, often white dwarfs, so they're pulled apart by the gravitational field of their star, and we can see the effect of chunks of the planet falling onto the star that pollute the emission spectrum of the white dwarf. They are usually clean, but if you have rocks mostly that have fallen onto the white dwarf, you would have some absorption line on top of the emission spectrum of the white dwarf. So these are the kind of things that we found by looking elsewhere. That is how exoplanetary science really is a game changer. But how do we detect and study these planets? Well, I'm sure you're used to thinking of planets and envisioning features of them, the rings of Saturn, the band and the zones of Jupiter or the storm. Slightly different when we deal with exoplanets. I know the field is really cool and we have pretty posters, but it's because we have to compensate for the fact that we cannot have this kind of images. Because you can take the biggest telescope that we have and zoom on an exoplanetary system, all you get really is a few bright pixels on a detector. So how do we get to study this planetary system with such definition while all we get is a bright dot? Well, fortunately, the brightness of that dot changes over time as well as over wavelength. I'm going to show you what we can get at the highest level by looking at this monitoring, and then we're going to get a bit deeper through the talk. When we look at how the flux coming from the system change with wavelengths, and you can see at the bottom there, it's the emission spectrum of the star that appears to be shifting to the blue when the star is moving towards us because of the Doppler effect related to its motion on its orbits due to a companion, a planet, or to the red when it moves away from us. We can get insight on obviously the period of the planet, owing to the period of the shift, blue redshift, but also the mass, owing to the intensity of that shift. And then when a planet passes in front of its star, it's another technique called the transit technique, then we can look for flux drop. So again, one bright dot in the detector, and when the planet masks a bit of that star, we don't see it, we just see the flux drop. The flux appears slightly less bright, and that relates to the planet to star area ratio, so we can get the radius of the planet. Great. And so in some instances, going into the years 2000, a few planets had mass and radius measurements. So for them, we could start discussing their density or their bulk composition, right? Which is great. But if we really want to start looking for signs of habitability, really get insight into the climate of other worlds, some of which have atmospheric temperature of a few thousand kelvins, then we need something else. And that something else is, there are a few techniques, this one is the one that is the most potent, is transmission spectroscopy. And this technique are looking at how the light going through the planetary atmosphere, which is shown here on this image as a gray, slightly translucid ring, is affected when it goes through that atmosphere. So, looking at the graph that follows, that's going to explain this a tiny bit more, we see that if an atmosphere is not really absorptive at the wavelength λ1, but very absorptive at the wavelength λ1, but not so absorptive at the wavelength λ2, the transit depth that you're going to have, which is shown as the bottom, is going to be slightly deeper at λ1, because here you have the extra contribution of the atmospheric annulus at this wavelength. You have a tiny bit more flux blocked during the transits. So if we turn now to an actual data set from the Hubble Space Telescope on the right, what you see is a transit depth that increases for this exoplanet HD 209458b, that increases around 1.4 micron by a few percent, meaning that there is something in the atmosphere of that planet that increases the transit depths around 1.4 micron. So if you turn to your spectroscopic expert, you'll be able to say relatively quickly that what must be happening in the atmosphere of that exoplanet, which is a hot Jupiter, so it's okay if we find water there. It doesn't mean that there is life, is that there is water absorbing the light of the star at 1.4 micron. So we can start doing detection of atmospheric constituent through this technique. Now that we've talked about transmission spectroscopy, I would like to start bringing the comparison between HST and the James Webb Space Telescope. I'm sure you're all familiar with this picture of the Carina Nebula with HST. I'm going to put it next to same picture, but from James Webb. And you can see with a level of detail, the information content with James Webb is substantially higher. We can see this by eye. So I wanted to make this transition before coming back to transmission spectroscopy and highlight what will be the key differences when we go from HST to James Webb. This is the first transmission spectrum that has been released, not the first, sorry. This is the first molecular detection that has been made with James Webb. The molecular detection of carbon dioxide in the hot Jupiter WASP-39b. And the carbon dioxide, if you're wondering where it is, relate to this strong increase in transit depths around 4.3, 4.4 micron. That's the first time it was detected. Now, in order to showcase the game-changing property of James Webb, I'm going to take this plot, shrink it, it's going to look terrible, and put it next to what we've had for that planet prior to using James Webb to study this planetary atmosphere. So this spectrum that you have here is a spectrum of the same planets before we had James Webb. You have here the same wavelength range that I showed you before. You have a few data points here that were obtained with Spitzer, which is a telescope that was working in the infrared, that was not in an orbit around the Earth, but actually in a heliocentric orbit. And I'm going to now put on top of this spectrum the one that I just showed to scale. So I have to keep on going back and forth between annotation and moving slides. So this right here is the data that has been obtained in one transit with James Webb. And what you can see is a substantial increase in precision, right, between these data points and what was acquired before with HST. Two things can be highlighted. First, the decrease of error bars, which are shown here, and also the increased sampling, so the number of points per wavelength bin, which really allows to map the molecular feature that we see here of CO2, to really map its increase and its decrease, which has a lot of information that I'm going to show you in a second. Question? No? We have a new person coming in. New person coming in. Okay.
I have a quick question. In these plots that are associated with water, can you also tell the phase of the water? You know, what, or is it always just a gas? Or
yeah, so it's transmission spectroscopy. So in this case, everything that we see is in the atmosphere. So all of that is in its gas form.
Thanks.
Yeah, you're welcome. So one last thing I wanted to mention, I've highlighted the fact that James Webb provide much higher precision on the measurements, allow for higher spectral resolution that enables us to map these absorption features. And now the next thing that I wanted to showcase is the fact that James Webb also provides us with a much broader spectral coverage, because the data that I'm showing you on the right is actually only part of the data that has been acquired for the planets. So look at this red rectangle. This is typically what we focus HST on, this 1 to 1.5 micron area. And this is what we expect to get for the best James Webb targets. This whole wavelength range that really allows us to get all these different molecular features. So we've talked about CO2. Oops. We've talked about CO2. That is showcased here. We can look at methane, extremely high resolution, through these wide spectral coverage, we can disentangle between, you see here how, just here, how both water and methane are contributing to this feature. If we don't manage to observe methane in a wavelength range where water does not contribute, then it's difficult to say if it really is methane that we're observing in the HST band or water. So the more wavelength coverage we have, the easier it is to disentangle between the contribution of different molecules. But it also is easier for us to find new atmospheric species that are not really expected. So that's what James Webb provides us with. In summary, exquisite data quality, high spectral resolution, and an extended spectral coverage. So through this, I hope you get the point that indeed exoplanetary science and James Webb are game changer. So what's ahead now? And what about exoplanets? Well, so far I've talked to you about the first steps, how we get from a planetary spectrum that we observe with Webb, and then we break the light apart and we can start doing identification of molecular features on that spectrum. But there's much more information in that spectrum than just being able to label molecules. And what's really interesting is the next step. If I can move to the next step, as I'm actually annotating. When we start decrypting or translating that information into actual atmospheric properties. What is the temperature of the planet? What are the abundances of the key elements? And that is what is shown on this figure from a paper that I wrote with Sarah Seeger back in 2013, which was actually part of my PhD thesis, that looked at how precise we could get with the number density or abundances of molecules through mining the transmission spectra of the James Webb Space Telescope. So what you see here is synthetic data that we were simulating at the time, and then retrieved to get, for example, here in green, very, very tight constraint on the abundances of methane, of CO2, and so forth. Then we can go further. We can constrain really well the pressure profile. This is the atmospheric scale height of the planet. The pressure at which we do have cloud layers, if there's any, the temperature profile, and so forth. So this is just to tell you that there's much more that can be done with the spectrum than just labeling features. We can actually start extracting important constraint on temperature, pressure, composition profile of this atmosphere, which can reveal photochemical processes, imbalances, and that is really the type of insight that we would have at hands with James Webb. To highlight the difference between James Webb and HST, I wanted to show this plot that was published back in 2018 that really show the extent to which the constraint we can get on metallicity, as well as, so metallicity on this end, as well as C2O ratio, both of which are important to discuss planetary formation and atmospheric evolution, gets to be tightened, much more constrained when we go from James Webb to HST. What you have here are the, if you wish, the confidence interval for these values given a certain data set, and you can see how moving from James Webb, so from HST to James Webb, from red to blue, really tighten these constraints and really allow us to start disentangling between different formation and evolution processes. Thank you for being patient as I keep on moving between annotating and changing slides. All right. The other thing I'm really excited about, that I'm sure you will resonate with that, is the fact that we can actually map exoplanetary atmospheres. What do I mean by mapping? Remember that the only thing that we see from an exoplanetary system is one bright dot. And yet, already back in 2013, for this example, we were already able to get constraints on the longitudinal distribution of brightness for planets, the one on the left, which is compared to Jupiter here, and we showed that it has a non-uniform cloud coverage. And through this demonstration, I'm going to explain how we got to that later, just on the next slide, we started to be able to discuss what's happening in the planetary atmosphere. So through this simple longitudinal constraint, we got to show that what's happening in these planets, that we do have hot parcel of air that are brought thanks to supersonic jets on the equator to the night side, where the temperature drops enough for clouds to form, and the clouds are brought from the night side to the day side. On this end, the cloud coverage is reflecting the light from the star, which is something that we can detect, up to a point where the parcel of air has reached close to the substellar point and it's getting too hot, and so the clouds get diffused. Into the next slide. The way this was constrained is by looking at how the flux that a planet is, in this case, reflecting during its orbit, when it does one rotation upon itself, changes with the hemisphere that is visible. And what we saw was that the hemisphere that was the brightest was just after a secondary eclipse, right here. So sorry, the annotation are just not working, which allowed us to get to this map that you have here, and that relate to the artistic view that was shown just before. But what is really allowing us to get to the next level is not this type of longitudinal mapping that we did back in 2013, 2014, but rather eclipse mapping. Eclipse mapping aims at looking at how the flux from a planetary system changes when a planet passes behind its star. Because when a planet starts going behind its star and then reappearing from behind its star, it's actually being scanned in different directions. And so if we monitor the flux carefully during the ingress and the egress, we can start getting constraint on its longitudinal and latitudinal brightness distribution. So we can recombine these scans to create a map of the planets. And we can get to 3D when we account for the fact that how deep we see in the planetary atmosphere is actually wavelengths dependent. So we get longitude and latitude from the ingress and egress of eclipse, and then we get depths in the planetary atmosphere. So we can start building 3D maps of the atmosphere of other worlds, which for some exoplanets with James Webb we'll be able to do at different epoch. So we can look at 3D structure in the planets, in the atmosphere of exoplanets, and see how they evolve over time, which is pretty much weather forecasts for exoworlds. And this is what we can use as a feedback loop for the atmospheric, global climate model or global circulation models that we have here and that we're using here for Earth and for planets in the solar system. But what is the type of homework that we still have to do before we really start the party with the James Webb data? There are a few effects that will make the interpretation of the James Webb data difficult. And we're going to talk about them at the high level, keeping time for as many questions as we can after. First one relates to the stars. Stars are actually not an easy thing to deal with. When we do transmission spectroscopy, we usually assume that the star is uniformly bright, and so what is being masked by the planet is the same as the rest of the star. So we're working in relative, but really it usually isn't, owing to spots, faculae, and not accounting properly for them tend to lead to perturbed, affected, biased planetary spectrum, and can this also bias the inferences that we make on the planetary property. So improving our stellar models and the way we model and correct for stellar contamination is going to be key to ensure the maximum return on investment of the James Webb and the extremely large telescope. Another aspect that starts really playing a role is the fact that planetary atmospheres are not 1D. For example, for hot Jupiters that I've mentioned, they are tidally locked, just like the moon is with the Earth. So they always show the same phase to the planet. So there really is an evening terminator and a morning terminator. So starting to account for the 3D properties of exoplanet atmosphere is essential when we do our retrievals. Not doing so tend to lead to strong biases. So we need to complexify in an adequate manner the model we use to analyze the data, because the one we were using for HST are not going to be good enough for James Webb. This is why it's so compelling to be in a department like EAPS, where we actually have atmospheric experts that can help us find the balance between full-on GCMs and the tiny toy model that we were using, 1D toy model that we were using so far with HST as astronomers. The last bit that I wanted to talk to you about, which relates to a paper that we published last month that was in MIT News with a student, Prajwan Nirula, is a paper that looked at what do we really know about opacities? Opacities, which are the database or the model that define how light and matter interacts in different circumstances, temperature, pressure, background gases. And what we realize is that, unfortunately, for a lot of the gas that we are going to observe, there's very little we know about cross-broadening. How is carbon dioxide broadened by hydrogen? We know pretty well how things work out when it's broadened by air or in certain circumstances. But the further we move away from Earth-centric condition or solar-centric condition, the trickier it gets. And so what we ask ourselves is, how far off would we be if we were to not account for effects that we think may be there? And so what you see here are the posterior distribution, or if you wish, the confidence interval. Let's say here on the top left, just to focus on one, shifting to annotation. Thank you for your patience. What you see here on the left is the retrieved temperature for different opacity models, all of which may be right. The true value that was used to create the synthetic James Webb, or synthetic or simulated James Webb data is shown with a dotted line. And you see that there's a wide range of values that do not agree with each other that are retrieved when we start tweaking the opacity model to account for the range of values or assumptions that we should be using for opacity models. So the bottom line of that paper was that we need also, in addition to improving our stellar models, in addition to improving atmospheric model, we also need to spend quite a bit of time to improve our understanding of light-matter interaction in circumstances that are quite far from what we used to here on Earth and in the solar system, in order to optimally decrypt, translate the spectra from James Webb, and thus make the best of these multi-billion-dollar facilities. All right, with that, I think you have all the takeaways. You are now well aware of why it's totally okay to be excited about where we're at and why this new era of astronomy matters so much, because it really brings some of the fundamentals, some of the things that relate to the public, life, habitability, climates, back at the center. Now you know how we got here as a field, as a exoplanetary science, in terms of technology. You understand why and how James Webb and exoplanetary science are game changer, providing us with new perspective on planetary system and the processes underlying them. James Webb providing us with exquisite data set, high spectral resolution, and a broad spectral coverage. You understand what's ahead of us. Remarkable constraint on temperature composition and pressure profile for a wide range of exoplanets and atmosphere. The fact that for quite a few of them, we'll be able to even map 3D structures, temperature, composition, structure in the atmosphere. But in order to get there, there's quite a bit of work to be done. We just have to up our game with regard to modeling so that we can correct for stellar contamination, account for 3D effects of atmosphere, and most importantly, translate adequately the spectral information that we have in the data sets. And so with that, we'll be able to reveal the world and gain new vantage points from which we can look back. And I leave it at that to see if there's any question and we can talk a bit more. Thank you.
Thanks very much. That was fantastic. Do we have any questions?
This is Dave Orton speaking. I have a question, and you'll have to forgive the naivety of this question, please. I think all of us amateurs are familiar with the Drake equation and the various terms in the Drake equation, some of which are highly speculative and vague. 0.5, knowing nothing better. Is there any sense in which the James Webb Telescope and the studies that it makes possible allow us to sharpen the uncertainty associated with some of the probabilities that feature in the Drake equation?
Yeah. Yes, it will. So James Webb 1, on the one hand, but also the telescope that allows for there's multiple layers, as you said, multiple parameters related to that equation, and new formulation of this equation have been proposed since then, including one, I think, by Sarah Seeger here at MIT. One aspect relates to the occurrence of these planets, and mission like TESS that has been led by MIT really helps tightening that. And then for what relates to the occurrence of terrestrial habitable world, this is where James Webb is going to start to make a first dent at that parameter. So only a handful of planets will be characterizable in that regime. And the reason for that is, with the current technology, the only terrestrial temperate planet that will be accessible with James Webb are those found around tiny stars like the TRAPPIST-1. We don't have, James Webb won't be able to characterize terrestrial world found around sun-like star. The planet to star area ratio is going to be too small. And this is why, I wanted to show that earlier, this is why we started deploying a network of telescopes called Speculos, and you have one of them here. So this is one that we built back in 2018-19 on the island Tenerife, which is one of the Canary Islands of the coast of Morocco, and you see Teide, the volcano that's just here at the back. So these are missions, this is MIT telescope. These are missions that are specifically looking for terrestrial planets around these ultra-cool dwarf stars, because there might be a handful of them, a handful of systems, but they are the one for which we can really use the James Webb Space Telescope for this type of research. And in fact, I think we're spending about 11% of all of James Webb's time allocated to exoplanetary science on that one system already. So this is
On the TRAPPIST system?
Yeah, exactly, in the TRAPPIST system. That's how precious these systems are.
I'm curious what the process or the politics are to getting data from your favorite system. Was there, how much control is there over where James Webb is collecting data? How do you vote?
Yeah, that's a great question. Maybe I can talk about how we proceeded with Hubble. So for the TRAPPIST-1 system, I led the atmospheric study of the TRAPPIST-1 system. So the way it worked out is we made the discovery, we knew about the system, and I contacted the director of the Space Telescope Institute, and there's director time. So when you have high potential targets, you can convince the director to allocate time on the telescope. Same thing with James Webb. However, for cycle 1, time has been allocated through what we call guaranteed telescope time. So for the people who contributed to building the telescope, the teams have guaranteed access to the telescope, and they can choose to do whatever they want. And naturally, they spend quite a bit of time on James Webb. And on the other side of that, there was a first call for cycle 1, which is about a year and a half long. And you can write your proposal, it is reviewed by different panels, and then time is allocated.
And does that have to then be coordinated with, it has to, I guess, with where exactly the telescope is all the time? Gosh.
Yeah, that's a great question. Because James Webb work in the infrared, it looks like this spaceship, this sailing boat, correct? It needs to be the layers that you see that are as big as a tennis court are actually shielding James Webb from the sun. So there's only so much of the sky that you can look at a given time. So yeah, there are windows where, unless you are in the continuous viewing zone, then there are windows during which you can observe certain targets. Yeah.
There's one question in the chat. Patrick, do you want to ask it out loud? I'll read the question.
No, I can do it. Sorry, I was
great.
folding laundry while I listened. My question is, what, if anything, would be a wow signal from James Webb Space Telescope study of an exoplanet? Like something that would make people take the time to look even more.
Yeah, that's a great question. My number one answer to that question is what we would call a technosignature. Not just a biosignature, but the presence of a complex molecule in an atmosphere that we can't explain without the presence of some form of advanced form of industry. Think about finding CFCs in Earth's atmosphere back in the days, right? This type of things. But for that, we need to really up our game with regard to opacity models, because it's not unlikely that we find absorption features that we can't explain, but we won't be able to say what molecules is behind them until we do the quantum physics work. So that's where the homework needs to be done. So the wow would be that. A signature that isn't just a biosignature, it's a technosignature, a molecule that we can explain without advanced processes that aren't just biological processes.
We have one write-in question. To probe an exoplanet atmosphere, how large does the planet radius have to be?
So that depends on the star and the telescope that you have, really. So right now, you can do Earth-sized planets around late M dwarf. You can do super Earth around even up to a sun-like star. So most exoplanets can handle. The terrestrial one, we need to go to small star. These are the ones for which we have the constraints. For the rest, we can do most of them.
Julien, was MIT involved at all in, the design of the telescope or specifying any of the tools?
For James Webb?
Yes.
It's a great question. I should know that. I don't. Sorry, this telescope has been planned for a long time. In fact, I was planning when I started my PhD at MIT to use the data of the telescope on the last year, to start in 2011. I was wrapping up early 2014. So I was planning on having data back then already, 2013, 2014. So that's how much delay it has gotten, but it started 20 years before that. So I don't know to what extent MIT was involved. I don't think much, to be fair, besides providing the scientific papers that allows for the community to get a grasp on what may work, what may not work, and where we should focus our efforts. Besides that, I don't think it was involved. It was involved for tests, but it was clearly the ship, technological development, and so forth.
So I'm curious what form of the data you actually get, and I'm also curious about the dynamics. How long before you can get your hands on data from James Webb? But also, do you end up just with a few pixels in their brightness as a function of time, or are they these sort of still shots? And then how long does it take to process it into those spectra?
Yeah, great question. So typically you get access to your data almost on the same day. So that's a first layer of answer. Then the data that you get is acquisition of the field where you see the stars, and then the grism or the prism is put in place, and so the light is split. And you have the dot that becomes a line. So that is your spectra, and for each acquisition, you have an image. So you have the flux in different wavelengths as a function of time. So you can extract that. Extracting the spectra is not, beside the fact that James Webb is a new telescope, so there's a lot of what we call instrumental systematics that you have to account for. For example, the response to one photon may not be the same over the course of the observation. You might have a ramp. Initially, the quantum efficiency might be lower, and then it plateaus, and then you have an asymptotic behavior. So that's, for example, the type of thing that you have to account for. So we are, as a community, at a stage where I think we now have our tools together. Now that we have real data, after a few months, we know how to handle this data. So now the bulk of the work is really interpretation. Once we have a spectra, how do we extract, how do we convert the spectra into constrain on planetary properties, as I was showing before, atmospheric properties? And how do we start accounting for the limitation of our own models? These limitations that were hidden when we were dealing with HST, with Hubble, because the quality of the data was, I don't want to say so bad, it would be unfair to HST, was good enough to hide the limitation of our models. But now it's clear that, okay, we clearly have to improve on our end to interpret properly these spectra from James Webb.
And the nature of the error bars, I'm realizing I didn't understand. So in the spectra, you pointed out the error bars. Is that from repetitive images that are done just back to back, or across different days, or?
Yeah, great question. So the process of emitting light is a Poisson process. So the amount of light you're going to receive, to the amount of photons that you're going to receive from your light bulb, is not constant over time. It has a certain distribution, and that distribution, or the relative width of that distribution, relate to the intensity of the target. And so that's how you can relate the uncertainty on your measurement to how much photons you're actually getting. And that's just Poisson statistics. But on top of that, technically, you also have, so that's white noise. Poisson statistic is white noise. So that behaves wonderfully, and it scales down. The more photon you get, the more signal to noise ratio you have. But then on top of that, you have what we call red noise, noise with some structure, and that's systematics and so forth. So that's what needs a bit more work. And usually you have a combination of both in these error bars.
So the proposals that you submit to get different images also might include the exposure time?
Totally, yeah. You have to demonstrate that you can, this is the science you want to get to, and these are the measurements you're proposing, and they are just enough to get to the science, but not redundant, because you don't want to waste these resources either. So, yes.
Another question. You've shown evidence of the spectra of some simple molecules, CO, CO2, and so forth. And you mentioned in response to an earlier question, it would be a real game changer if we were to detect higher molecules that we could not explain the presence of by any simple means. Is it a question of we don't have the resolution yet to be able to detect the spectra of higher molecules, or is it a matter of we just haven't seen them so far?
With James Webb, we have what we need to some extent. It depends on which planet. Like for the TRAPPIST-1 planet, it will take a lot of hours to get there, but we can do it. But that's going to be to get to what we need. It's going to be 2+ years from now of really investing. Right now, the programs, I mentioned 11% of James Webb time will be on the TRAPPIST-1 planets, but that's just going to be scratching the surface. And in order for us to get to what we need to find molecules to study planetary atmosphere of terrestrial planets, it's going to require the community to get together and ask NASA hundreds of hours on the planets, which is fine. It's going to be done, but I think we still need to get together to get to this level of understanding, and then spend the time. As we're going to have to spend the time to improve our stellar models, as we're going to have the time to spend the time to improve our opacity models, I think I can confidently say that even though we need to keep on obtaining data with James Webb, it's not unlikely that it's going to be only 2 years from now before we really make the best of these data sets. Like we're going to have a few studies coming out and doing some interpretation of the data, but to really mine them to the fullest extent, we're going to need to improve quite a few of the models I've mentioned before, and that's going to take time. And only then we'll be able to go back and be, okay, now the analysis is thorough and complete, and we can get to a more precise constraint on these planetary parameters.
Yeah. So there's some richness and depth to the data acquired so far that has not been, in your words, fully mined yet.
Correct.
Seems like that'll be a real challenge since everything's moving, right? So you can be collecting data for 2 years, but everything's shifted, right? So you have to have some sort of alignment strategy to be able to average effectively.
And the real trickiness is to account for the fact that there's politics involved. We all have incentives. Like, we do want to have this big impactful paper, and sometimes acknowledging the limitation of our models may prevent us from having this big claim to make. And maybe even acknowledging that may allow for other fields, let's say cosmology, for example, to say, oh, people in exoplanetary science are not ready to deal with the James Webb, so why don't we take all of their share of the telescope and do our own things? So it's tricky to be able to say, well, we have to keep on observing because we don't know what's going to happen to James Webb. Like, if we just wait to do exoplanetary science when we're really ready with our models, well, maybe something happens to James Webb. I hope not, but maybe something happens to it. So it's just being mindful of that, keeping on moving forward, making sure that the field understands that we have to keep on getting this data, even though we may not mine them to the depths that we will be able to in a few years from now. So it's dealing with these competitive incentives that's interesting.
We have any other questions? Yeah,
Yeah,
Michael?
this is Mike. I have a question. It's one of those questions, and maybe obvious to everyone but me. How do you know where to start at time equals 0? For example, when you were looking with TRAPPIST, what was the thing that took it from being just a point of light to something you really, really wanted to study? And is it a matter of doing a whole suite of tests to do that, or just one or two to screen them?
Yeah.
Or how do you get that initial enthusiasm?
Yeah, that's a great question, actually. Let me see if I have what I would like to show. I might have to open another PowerPoint, so if you can just bear with me for a second. So for the transit technique, what starts the trigger is the following. So we look at, for speculoos and the TRAPPIST, TRAPPIST was a prototype for speculoos, okay? And so the TRAPPIST was looking night over night at 50 M dwarfs, which are these tiny stars that are spread over the skies. So we picked the 50 brightest, and you would be looking at one for a night, a few nights, and then moving to another one, and then to another one. And what we were looking for is these flux drops if something happens to pass in front of it, right? So back in 2015, the first one happened, and we could not remove it by explaining, a cloud or some instrumental systematics, and that was the first flag. So let's spend more time on it. And spending more time, it was clear that something was happening. And that led to the first paper where Nature back in 2016, where we showed that there's at least 3 planets in the system. With that, we were able, so I got time on May the 4th, be with you. On May the 4th, we got Hubble to look at a double transit. At the same time, planet B and planet C were passing in front of the star, and I could use this data to show that the planet don't have this thick, puffy, hydrogen-dominated atmosphere, which you have on one planet, what we call primordial atmosphere. Because these are thick, it's easier to detect, and we could see there was a flat line, so there was no sign of a big, puffy atmosphere. In the meantime, we got to convince NASA to use a Spitzer Space Telescope to look for 20 days, stare at the system, and look at everything that would pass in front of it. I wish I had data here, but I have it in other slides, I'm sorry. So for 20 days, we were expecting to have 7 drops or so over the course of the first 10 days. And the PI of TRAPPIST, who is a friend in Liege, was, I think, stuck in Morocco, and he had no connection. So I ended up having the data, and he asked me to mine them. So I just quickly mined them. And then the light curve shows an insane amount of transits, meaning way more planets than I expected. Like we were expecting 7 flux drop, and there were like 15 or so. So clearly there was more than 3 planets, and it was quickly estimated it was something between 6 and 8. 7 was the right number, but that's what matters. That's how things unfold. And it was over the course of a whole year. It took us a whole year to get to proving that there was 7 planets in the system. Just flux drop. That's the only thing we're looking for. And as they're periodic, you get to attribute 1 to the same planets. The depths also allows you to. That's a tricky thing. When you have so many planets, it's tricky to know which one are which. So depths gives you the size. Some of them have the same size, so it's a bit complicated. But then, if you observe long enough, you can reveal the structure of the system. What's fascinating, I mean, I can keep on talking about this, so I want to leave room. But one thing that's really fascinating about this system is that the system is about 8 billion years old, and so almost twice as old as our own system. And it's tightly packed around the star. You've seen compared to just the orbit of Mercury, right? And they are all locked in triple resonance chain. So there's ratios of integer for the orbital period of each planet with one another. So people have used these ratios of integer to do some form of music out of this orbital configuration. So it's really like a Swiss clock. So you have to think about the formation and evolution processes that have allowed these planets to just come together and really go around. It's quite remarkable. Anyway.
Thank you very much. I appreciate everything you've said today. Thank you.
My pleasure. I'm muting myself to leave room for other people to ask questions.
I have a quick question of local interest. You showed the image of, was it J1407 with all the rings, and a group from here in Rochester was involved in describing that. I'm just curious if there are any updates on that planet.
Yeah, I actually don't know, but I love considering what to do with James Webb about that one. Through this term, that would be really interesting to look at the gradient of composition through these different rings with James Webb during transit. So I don't know if that's possible, but I'm happy you pointed at the system and through this connection with Rochester. So thanks.
Does anyone know where it is? I think it's hiding, right? Or does anyone know where this planet is at the moment? Or, I don't know.
Yeah, it should still be at the same place.
Oh, okay.
That's actually a good point. I don't remember the orbital period, but it passed. I will look into this for sure. Thank you.
Yeah.
All right, folks, I think we should probably call it an evening. And so, Julien, thank you so much. Maybe we can promise to invite you back when you make your next big discovery.
We look forward to hearing about the TRAPPIST system in 2 years. Yeah.
All right. So we really appreciate it, and our best wishes for your continued success. And on behalf of the Club of Rochester and the Club of Western New York, thank you so much.
Thank you very much. I really appreciated the invite. And for those that are interested in getting to know a bit more about what we do, because we do more than just exoplanetary science. For example, we develop technique to map the insides of asteroids during close encounter. There's more than what I just talked about that we do. I would invite you, if you're interested, to just stop by our website that has recently been renovated. I just put it in the chat. So you'll get more insight into the type of science and techniques and the people that work with us. All right. And if you have any other questions or comments, feel free to send an email. I'm always happy to answer. Thanks again for the opportunity, and thanks for all the great questions. It was fun. Appreciate that.
Great. Thank you very much.
Thanks very much. Yeah.
Bye-bye.